Nice to see everybody. My name is Ryan Wright. As Mary said, I work at that. In 2014, I created the open source library Quine, and that's the subject of today's topic. Today's conversation about Quine.io, and especially using it for streaming graph search. So before we get started, I feel like I should call out the elephant who's not in the room. This is not a talk on LLMs. But maybe even a little bit more to the point, this is a talk on not LLMs. Because if you want to understand a complex new technology, one of the best things you can do is understand its limitations and what it can't do. And there's a lot of good research coming out right now about what LLMs can't do, especially around graph-related tasks. If you look a little closer, there's some interesting hacks you might try to really shoehorn in some graph problems on your LLM. But in truth, we're learning that while these things can generate text amazingly, they're really not very good at reasoning and definitely not very good at graph-based reasoning. So all the graph challenges that we've had before still remain highly relevant for modern data pipelines still in the world of LLMs. Those use cases run in so many different directions that we could probably do a whole talk on just things that we can do with streaming graphs. But in particular, they fit nicely into pipelines for the sake of feature extraction to train other ML models, to do complex event processing to find patterns on streams coming in, working on recommendation systems so that you can propose, a related content related to something a user is looking at, implementing different algorithms. We'll hint on or talk about this in a little bit. But incredibly powerful algorithms become very simple to apply when you take this streaming graph perspective. Entity resolution, you want to combine multiple things because there's really supposed to represent one item. And even on the cutting edge, our team at that has been working on new kinds of anomaly detection, especially for categorical data that is enabled by streaming graphs under the hood. So use cases just kind of run in every direction. We'll look at a couple of them here. But really, if we step back for a moment and talk about stream processing, streaming data, and graphs, we can think about this in two different ways. A lot of times, streams and graphs, they go together really nicely, but they're thought of as, like the graph is kind of the railroad track that the data follows. So if you're building a streaming data pipeline, you're probably going to build some form of a graph, probably a directed acyclic graph, so that your data can flow from its source through all of your microservices to get to its end result. That's an example of the stream as the graph. The data follows the tracks and gets through to the other end. But another view of a graph in a data stream is really the data itself represents things we want to connect together. The data itself is the graph. And that's really what I want to start focusing on here right now. And then if there's time, we'll flip this around and look in the other direction. There's a common misconception that graph data is a special kind of data. Some data is, some data isn't graph data. That's not true. Actually, all data is graph data. And when you take something like a JSON object out of your data stream, and you think about what that is supposed to represent, it starts very naturally turning into a graph. So in this case, this first example is looking at a cybersecurity related task. So what's happening on a machine? What's happening on a computer? Well, we've got a process. It has an ID, 3689. It is writing to a randomly named file in the root directory at a certain time. So we can represent those things that we care about in a graph. Nodes and edges, that lets us describe what this event is referring to. We've got a node to represent process 3689. We've got a node to represent the event in green, that there was a write at a certain time. And then there's a node to represent that randomly named file down at the bottom. Next event streams in through your pipeline. All right, it's related. Same process ID, read event to the same file. Update the graph, and we keep going. Same process ID, now we've got a network event. That process is sending data out the network. So we create a node to represent the IP address. In this case, this is the local IP address that's bound to, and include the timestamp on the event. And we're building a graph out of the stream itself. When we do that, it starts opening up the world of graph analysis and a whole lot of insight that we can gain for what's happening in the stream because we're able to connect the dots and look at something beyond just one event at a time. We could even fold in a second kind of stream into this. So here's network flow data, maybe coming from a router or some other components in the network, saying I witnessed some kind of traffic from one IP address to another IP address. Great, let's put that in the graph too. We've kept a piece of what we had before, but now let's have a node to represent HTTP network traffic and then connect it to the external IP address that it was connected to. That lets us start reasoning on a graph built from the stream. We can say something about process ID 3689 having this communication with an external IP address now, because we've been able to take several events from the stream, represent them in their graph, and reason over that graph. So now the real dream is to do that at large scale and get tools that make it really easy to express what you want and query what you want. So I'm going to show you an example of using actually this cipher query to analyze a stream that is built into a graph. Cipher is a graph query language created by Neo4j. It's somewhat ubiquitous in the graph world, and it's very SQL-ish. So it's quite similar to SQL with the exception of that first match clause. So that match clause, think of that as ASCII art. We're drawing a picture of a graph. The things in parentheses are trying to draw a little node, and then the dashes and greater than, less than signs are drawing arrows to connect them. That's the pattern we're looking for, and then we're adding some constraints down below it. Every time we find that sort of a pattern, we're going to trigger a certain kind of event. So instead of trying to help imagine what this looks like, I'm going to just show it. So let me drop out of slides. And over here, I have a console, which guarantee will be hard to read, but we don't need to do much of that. This is the open source website, so quine.io, where you can go download and do literally exactly everything I'm doing here, because I'm going to run java-jar. I'm going to give it the Quine jar downloaded from the website. I'm going to say -r for recipe. And I'm going to run the apt example. So this is a recipe over on the right-hand side. You don't have to read this. I just want you to know that it exists. On quine.io, a recipe built for doing exactly everything that I'll show you here. Let's go ahead and start this and run it. That starts up Quine, starts consuming from two different sources of data. So we've got our network source, we've got our local event source, and over here on the, I'm going to shrink this down a little. And I'm over here, let's explore a little bit. So we've got data that looks like what we were talking about. We've got some network data there. We've got some process data here. By the way, this is all synthetic data, but it is based on a true story. Quine grew up in its early days funded on a DARPA program aimed at some very hard cybersecurity problems. So it was created out of necessity to do this kind of analysis and others at scale when no other tools could really keep up. So these kind of examples that we're looking at here, we've got network traffic. We've got a process that had a read event to some file. We can explore around and see what else is in this data. So there are other events here on this file. There's other events connected to that process. Each of these is built out of incoming JSON streams. You don't have to understand this at this point. I just wanted to show you that each of those streams is building something. It's building into a big graph behind the scenes. And I don't know if you caught it or not, but over here on the left-hand side, we had a message printed out. That message, we're software people here, we can assume that printing something to the console is sufficient to demonstrate real-time actions taking place. This could be a Slack message, this could be an alert to another system. But in this case, it is the result of that cipher query that I showed you earlier, finding a complex pattern built up in the graph as it streams in real time. Let me show you what that looks like. So this is a link to all the relevant data that was a part of finding the pattern. I'm going to arrange it a little bit so it's a little easier to see and understand. this is what that cipher query was looking for. This is a process, in this case Excel, an Excel process that wrote to a temp file. That file was later read and deleted by another process. This process is named ntclean. That process sent data out the network. What we wanted to find in that graph that's built from the stream is suspicious activity where two processes communicate through some secret back channel. And so in this case, writing to a file, reading and deleting from another process, that is a very suspicious activity, and it's very difficult to find because it's spread out in time. These can come from different data sources that have to be merged together. You have to hold on to the pieces as you go. And if we want to, we can even explore around to understand the story a little bit better. So this was a malicious spreadsheet that was emailed to the user. They opened the malicious spreadsheet. That caused it to read some of the user's docs in their private plans document. As that data gets written into the miscellaneous.data file, it's read and deleted by this ntclean process. Where did that come from? Well, this process was started by an SSH process. That SSH process itself, get rid of that spawn one, that SSH process received data on a local network interface, port 22. Here, let's collapse some of these things. The other side of that communication here was an inbound connection from this IP address, which also, if we explore over here, happens to be the same IP address that it sent data out to. So the full story here is that this advanced persistent threat got into the system and then just sat quietly, waiting. And then when the email comes in from a spear phishing attack, the user opens it, thinking nothing of it. That causes it to grab some data, covertly write it somewhere, picked up by the APT, deleted, covered their tracks, got the data out the door, and all of this was spread out in time through streams, through several different streams that have to be joined together to actually see the picture and tell the whole story. So this is an example of searching the graph for that key underlying pattern that let us find this. And then when we want to, we can poke around and understand it a little bit better through exploration. So why is this so hard to do? As I mentioned, we created this over the last 9 years now out of necessity because we had to. There weren't really good tools for doing this, especially at scale. And the reason is because if you try to do this, you try to take a stream of data, you try to assemble it together so that you've got the thing you're looking for coming out the other side. You have to start with a stream and take one item out of the stream. That's not what you're looking for. So you've got to store it somewhere. Put it in a queue of unmatched events. So you take your A's, put them here, your B's here, your C's here. Store them locally so that you can have them ready for the next event that comes through. Maybe the next event will match. If it matches one of those ones that you're storing, great, now you've got new queues for those partial results. So save your A-B pairs here, your B-C pairs over there, keep caches of those things on hand so that maybe you can join them to the third piece and you can put all these things together. So meanwhile, you're accumulating lots of state that you've got to manage for all these partial results that you're building. And the typical approach is to do this probably in RAM, to hold these queues in memory, and accept the fact that you've got limited memory, so we'll just have a time window. We'll hold the last 5 minutes worth of data, for example. Anything that's older than that, well, we'll just expire it out of the cache and throw it away. The downside to this is that you'll lose results. If your matches spread out further than your time window, you'll never see those results. And so lost results are often unacceptable, especially for that finding a needle in the haystack kind of a situation. So, okay, well, we can do something else too. We could set up durable queues. We could write them to disk. Key value stores are good at this. We can take that data, shove it into key value stores, and then hold on to them for a longer period of time. Well, now our problem is that the architecture of the system implemented in these key value stores is tightly coupled to the pattern that you want to find. A product manager comes along and says, I want to tweak this a little bit. I want to change that. Well, that's going to take 9 to 12 months. We'll have to redesign the whole system in order to do that. So this is the underlying problem that has been dragging down our ability to take a stream of data, put it together in a graph, and search that graph, is that either we accept lost data from time windowing, or we spread out our patterns across the entire architecture. This is what Quine is meant to solve. So give that graph abstraction over the stream, because it's the most expressive data abstraction. Eliminate time windows, so we don't miss any results. Allow combinations of events anywhere in the graph over huge periods of time, and allow us to update what we're looking for very easily without having to reconfigure the whole architecture. That's why we made Quine. So under the hood, real quick, how it works, and I don't have enough time to go into detail, but I just wanted to mention, under the hood, the graph itself can model anything, but under the hood, it has a graph computational model paired with it as well. Nodes in the graph are backed by actors. Asynchronous message passing is how queries are done, how updates are done. All of those pieces of the puzzle that happen behind the scenes are implemented with Akka actors. Lots more to say about that, but in order to distribute this, we cut the edges. Nodes in the graph can get distributed across any number of machines in a cluster, and we do so by cutting the edges, as you see. One edge is really made up of two half edges, and the edges are stored together with the nodes. In Quine, there's this fundamental design principle that is pretty essential for streaming data, but it inverts the database assumption. So instead of saying it starts empty and we fill it up with data, if you've got an infinite stream of data, that's going to be problematic sooner or later. In Quine, all nodes exist. We start with the assumption that every node that ever could exist does exist, and what we're doing when we ingest data is we're doing what physicists call symmetry breaking. We're creating some structure in the graph that is useful for representing what we want to represent. Turns out all those extra nodes have no impact on the system. We can factor them out a lot. This is a conceptual design, and it inverts a lot of typical assumptions that allows us to gain some big efficiencies on the back end. Behind the scenes, all those real-time notifications were done with standing queries. This is a query that, just like you write a query, you issue it, you get a result back. You can take that same query, issue it to Quine, it'll stay live and active, and move itself, push itself through the graph, storing partial results along the way. And when there's a new match, that new match gets completed, you get notified immediately. So that's a bit about how Quine works under the hood, and I want to come back to this slide from earlier. So as we're talking about, the data is the graph, building that graph out of our streaming data events. I wanted to come back around and say, when we have this perspective, we've got this graph built out of streaming events. Those events and that graph that we've built can become the new railroad tracks, the new stream itself. And I want to show you an example of this in a second quick demo. I'm going to run another recipe. This recipe is the Ethereum tag propagation recipe. It's also available on quine.io, so if you'd like, you can run this yourself. What this does is this connects to the live blockchain, so we're going to test and see how good conference Wi-Fi really is today. This connects to the live blockchain, pulls in whatever Ethereum transactions are happening right now while I'm speaking, forms them into a graph so that we can then use them as the track on which to run events down. So let's take a look. Let's grab a few nodes here. All right, we've got a couple blocks. These are Ethereum blocks from the blockchain, whatever is happening right now. Live demos are always fun because who knows what's there. 3 blocks, we've formed a blockchain, that's great. Every block is mined by a particular account. Now we take a second stream that isn't just the blocks, but a second stream of transactions, fold those things together, and connect them together in the graph. This is a few more transactions than we'd like to look at the moment. So what I'm going to do is undo that, step back, and limit to just 3. All right, so we've got, interesting, this was a transaction that included the account that mined it. But if we look at a transaction, you can see it goes from one account into another account, and this is what the structure of blockchain data looks like. Looking at mousing over any transaction, we can see some of the details there. We're not going to go into any depth on those. But everything that is happening now and is about the transactions happening on the blockchain gets represented here in the graph, so it becomes available to us to use for our other purposes. Those other purposes are, I want to run a graph algorithm that lets me follow the money. If there's some nefarious actor in here that I'm suspicious of, I want to know, where does their money go? Maybe they're laundering it through the blockchain, it spreads out to lots of accounts, comes back together. Maybe I'm just curious who else they're associated with, and so I want to understand what's happening there. Well, let me find an account that has an interesting structure. And again, this is live data, so I never really know what we're going to find. But here is two transactions. I'm going to take the one that's earliest in the chain, and I'm going to right-click it and just say, mark this as tainted. This is just going to set a property on that particular node. But I left the console up because hopefully we'll see some notifications here as soon as we mark this as tainted. All right, we saw quite a few. I don't even know how many that was. What just happened is a standing query behind the scenes that is watching for any tainted account. And if it's tainted and there's a transaction into some other account, then go mark that other account as tainted and record how far away it is from the original. So what that does is it lets us, if I can choose the right things here. So the pink one is the one we marked as tainted. You can see now it has this little pop-up property that says tainted equals 0. And every outgoing transaction, in this case only the next one, also gets marked as tainted, shows up in red now. That's one hop away from the original account, tainted equals 1. Go further, these are all the transactions coming out of there. All of these are marked as tainted as well. And as money moves through the blockchain, if there are any more, we'll see them and they'll show up here. As it happens live, you'll see more notifications coming out in the console about money moving through the blockchain, and we're following that move through the graph. So in this case, we set a standing query to cause events, to search the graph and watch for anything that is newly a tainted account making a new transaction to any other account. When that happens, go trigger an algorithm propagation. So update the tainted tag, keep track of how far away it is from the original. This is an example of kind of using the data itself as the path, as the stream on which we're doing our processing. So here again, these are just a couple examples, and there are plenty more. But I wanted to give a quick illustration of when you can actually do search on a graph built from streaming data. You can get real-time notifications and propagate algorithms and other complex kinds of events. So these examples were all running on my laptop. That's all well and good, but they're small enough scale that I can reliably do this for a demonstration here. But just to help give a little color, the team at that works with commercial partners to help scale this to huge scales. And so this is the result of some testing that we did, published in a blog post recently, where we're scaling up to 1 million events per second. So that's 1 million events coming into the graph every second, building up a very large graph very quickly. Also with a standing query on that graph that is watching for a 4-node pattern. So patterns in the graph that show up occasionally, built out of 4 different nodes, and this is finding those and streaming results out at about 21,000 events every second. So 1 million events in, build the graph, monitor the graph for this particular pattern, stream those results out at 21,000 events per second. While doing that, All the numbers you see on the chart and down below are what happens. The green line is throughput, by the way, so it's how many events are being ingested. All the numbered events are what happens as we're pulling power cables, partitioning the network, and doing all the other kinds of reliability and failure scenarios that you need to test and prove out for building high-scale clustered systems. So there's short links on a bunch of these slides. That links to a blog post that goes into technical depth. I believe all that was done for something like $20-some an hour worth of infrastructure. So if you'd like to know more, I'd point you to the blog post. These are some of the reasons why last year when we open sourced this project, it was voted the best open source project of the year. Big thank you to the community of users for their feedback and their input. We'd love to have folks check it out, give it a look, see if it's useful in your project. If you'd like, here's a bunch of links that can help you do that. Quine.io is the website. It is free and open source. Go download it, play with it. If it's useful, let us know. There's a Slack channel in there as well. If you find it on GitHub and want to make contributions, that would be awesome. Add stars there if you feel so kind. And then there's a collection of links over on the right-hand side where you can see everything we're doing. With that, I think we have a couple minutes for questions, and thank you very much.
Can hear me? Oh, good. Thank you. So thank you, Ryan. That's really engaging. I almost actually forgot to check the time, too. It's kind of really good. So thank you. And so now we have a couple more minutes before the next session, so we can have Ryan answer a few questions. Does anyone would like, you have any questions here? Okay.
Yeah, Ryan, thanks very much. It's really impressive. The question I have is scaling this, right? In this case, you show the scale of certain patterns, but it's like anomaly detection. There are new patterns coming in all the time, right? Can you describe how you want to scale on the number of patterns, not just kind of the data with the single pattern, a single set of patterns?
Yeah, yep. Great question. So from our perspective, that scaling the number of patterns that you're looking for in a graph is a measure of how many standing queries are you running concurrently while data is streaming in to build the graph and everything else. We've tested up around 100 standing queries. I don't know exactly where the limit is. Part of the challenge of working with graph data is it often depends on the data itself and the use case. And so depending on some of that, your mileage may vary or your experience could be higher or lower than that particular number. But just so we've got at least some number to pin to the wall and help anchor some intuitions, we've tested up to about 100 standing queries concurrently running.
Great, thank you. Okay. Oops.
Thank you. I understand that this is basically a database, right? You're persisting all the events that go through the graph. Can it be the database of reference? Can I query the database, query your graph, not with CQL, but with regular SQL, just so I don't have to sort of duplicate the same data elsewhere in the relational database? Can you handle that, or is there a thought of handling that?
Yeah, great question. You can. We know of a bunch of users who do and have that use case. I didn't mention during the slides, but the way the persistence works is it's swappable on the back end. So Quine stores data. It can store data locally on the same machine, even just in the same process. Or for large deployments, we tend to store using Cassandra, AstraDB, ScyllaDB, those kind of tools on the back end for data storage behind the scenes. And so the durability characteristics of those systems is what Quine inherits. and it's meant to work in that swappable sort of fashion. So depending on the use case, you can choose if you want your data locally or saved in a Cassandra cluster on the network, for instance. But all that for, if you want Quine to be the database of record for this, yes, you can.
Anyone else have questions? Yeah. Oh.
You mentioned $20 per hour, something infrastructure cost. Can you break it down? What is it exactly?
Yeah, the scale experiments that we've done and the cost to scale it, I don't actually remember all the details off the top of my head, but the link near the bottom right corner that links to scale will take you to a blog post that goes in depth for the architecture, the implementation, all of that, the cost for different configurations, that sort of thing. But it was maybe $26 an hour is what I seem to be remembering, but I want to point you to that blog post for details.
Okay. Anyone else have questions? No? No. Actually, I have a question too. So for ingestion, right? So can you actually work with like Kafka, for example, Kafka Stream and Pulsar like that too for ingestion side?
Yeah, to ingest data, you define an ingest query that connects to streaming sources. So Kafka, Kinesis, Pulsar, all the typical streaming components, configure it to go read data out of those sources, and an ingest query that takes, like we looked at earlier, that takes each record out of that source, builds it into a small little component in the graph, and folds it together with everything else in the graph.
Very cool. Thank you.
And the same is true, by the way, for all the results. Here we were taking standing query results and just printing them to the console, but those can also be published to any of these streaming sources or published to Slack and some other things like that, so that downstream events can take the results and do something else with them.
Cool.
All right, thank you very
Great.
much.
Thank you.